So the first law of thermodynamics is often expressed as there is no free lunch. Now, at my kids' school, there is free lunch. You know, you go to school, you get lunch for free. But is it really free? Somebody's paying for the lunch, right? It's just not the people eating the lunch directly. So the first law of thermodynamics is the law of conservation of energy. And the way we usually state it is the total amount of energy in the universe is constant. There is a fixed amount of energy. You can't make more, and you can't destroy what there is. You can never make a system that will continue to produce energy without a source of energy. Have you heard of perpetual motion machines? Something that just moves on its own and it doesn't need a battery or anything, and it just keeps going and going, right? It's like, oh, cool, if we could harness that, we could have energy from it. You can't make a perpetual motion machine. They always have some hidden source of energy. With energy, you cannot get something for nothing. Thermodynamics, by the way, thermal referring to energy, dynamic, talking about things changing. It's a study of energy and its interconversions, how it converts from one form to another. So conservation of energy tells us that the sum of energy changes in the system and the surroundings must be zero. So if we look back to this illustration again, where we've got before and after, the total change has to be zero. So the total change in energy for the universe equals zero, which means that the change in the energy of the system plus the change in the energy of the surroundings adds up to zero. That means what was lost by the system was gained by the surroundings. None of it disappeared. It didn't get bigger. It's all the same. When we use this triangle, it's the Greek letter delta. That means change in, and it's always the final minus the initial. Sign matters here. You can have an energy change that's positive or an energy change that's negative. And so it's always final minus initial. So we talk about the internal energy of a system. That's the sum of the kinetic and potential energies of all the particles that compose the system. So any substance, any system you could define, like whether the system is this mouse or my pen or the chalk, it all has a certain amount of internal energy. Turns out that internal energy is very difficult to measure. The change in the internal energy of the system depends on the amount of energy in the system at the beginning and the end. So if something changes its amount of internal energy, we just have to look at what it started with and what it ended up with. And that's called a state function. A state function is a mathematical function whose result only depends on the initial and final conditions, not on the process used. It doesn't matter how you got there, it's just the difference between where it ended up and where it started from. So delta E is the final energy, the internal energy, minus the initial energy. If we look at a change in energy for a reaction, it's the energy of the products minus the energy of the reactants. It's always final minus initial. So to help us understand a state function, we're going to look at a mountain. So if you're at the base of this mountain at zero elevation and you're trying to get to the top to 10,000 feet, there's more than one way you could get there, right? You could take this path A that kind of snakes back and forth. It's not too steep, but you're actually going to be walking 12 miles. Or you could take this very steep path that goes straight up the side. That path is only 5 miles. The change in elevation is a state function. It doesn't matter if you took path A or path B. If you start down here and you end up there, your change in elevation is 10,000 feet. Doesn't matter how you got there. You could also take a helicopter and fly up above and come and land on the top. How far did you travel? I don't know. It depends on how much of the country you zoomed around to see. Your change in elevation is the same. It's 10,000 feet. That's what a state function is. It doesn't matter how you got there. Some things are state functions, some things are not. Is the distance you hiked a state function? No. The distance you hiked is going to vary depend on how you went. If you took path A, it's going to be 12 miles. If you take path B, it's 5 miles. Any questions about that? We use energy diagrams to help us visualize energy flow during a change because it's very nebulous. It's hard to get your finger on. So this is an energy diagram. This is what we're looking at. We're looking at a reaction where carbon dioxide gas decomposes into carbon and oxygen. So we draw internal energy as increasing on what would be a y-axis. There's not really an x-axis here. So here we have our reactant. It's carbon dioxide gas. And in the course of this change, we end up with carbon and oxygen that have higher internal energies than what we started out with. So there was an increase in energy. So if the reactants have a lower internal energy than the product, the change in energy will be positive. Where did the energy come from? How did it increase in energy? It had to come from the surroundings. If this is our system and it increased in energy, the energy had to have come from the surroundings. So here's our system. Its change in energy was positive. The change in energy for the surroundings was negative. So energy flowed from the surroundings into the system. If the reactants have higher internal energy than the products, now we're looking at the same chemical reaction, but we wrote it backwards. Here we're combining carbon and oxygen to form carbon dioxide. Our reactants now have a higher internal energy than our products. So in the course of this reaction, this system loses energy. The change in energy is negative. Where does the energy go? It goes to the surroundings. Do we care exactly which part of the surroundings? Usually we don't. So here the system lost energy, the energy went to the surroundings. The sign here is important, and this is where money helps us. So I did have $2 in my pocket this morning, but my son wanted it for lunch, so now I have no money at all. Oh, but let's use that. Okay, so I gave my son $2. I'm not sure what he's going to get with $2, but that's his problem. I gave him $2. I lost $2, right? That was negative. Money left me. What's his perspective? He gained $2. So the change was negative for me, it was positive for him. How much money was transferred? $2. I lost $2, he gained $2. Same thing with energy. If one thing loses 5 kilojoules of energy, the surroundings have to gain it. It doesn't go away, it just goes back and forth. Any questions? If energy flows out of a system, it all flows into the surroundings. Energy flowing out, the change in energy for the system is negative. Energy flowing in, the change in energy flowing into the surroundings, so the change in energy for the surroundings is positive. The change experienced by the surroundings is equal but opposite in sign to the change experienced by the system. If I gave my son $10, the change I experience is negative 10, the change he experiences is positive 10. It's $10. The sign just depends on which direction it went. It's like transferring money between your checking savings. These slides are a mess today, I'm sorry. Between your checking and savings accounts. If you put it into one account, it's positive, but where did it come from? It came from the other account, and over there it's negative. Does that make sense? Well, we talked about The fact that energy can be exchanged between two things, we're talking now about systems and surroundings, through heat and through work. Heat is given the symbol Q. I don't know why, but it is. Work is given the symbol W. That makes more sense. Heat and work are not state functions. Their value does depend on the process. The overall change in energy doesn't depend on how it happened, but the individual processes do. So we have this equation. The change in internal energy is equal to Q plus W, the heat plus the work. And here are the sign conventions, and these are important. So if Q is positive, that means the system is gaining energy. We're always taking the point of view of the system, and the surroundings is just everything else. So I'm thinking about me and the rest of the universe. What's it doing to me? If I gain energy, if I gain money, for me that's positive, right? When a system gains energy, gains thermal energy, that's a positive Q. If the system loses thermal energy, it's negative Q. Work. Positive work is work being done on the system. Maybe I go to a spa and I get a massage, right? Someone's doing work on me. Is that positive for me? Yeah, that's nice to have someone massage you, right? Negative is when work is done by the system. That's when I go home and wash the dishes, right? Because those darn kids can never remember. So that's negative, right? I am doing something for the surroundings. I am doing the work. So I hope that helps you to keep track of those signs because it's important. Delta E, again, the change in internal energy. Energy coming in is positive, energy going out of the system is negative. So let's look at this pool table again. So this is a nice smooth table. So this the surface is very smooth, and we have a ball here with an initial kinetic energy of 5 joules, and it's rolling. Now this is real, and so there is some friction between the ball and the table, right? A good pool table will minimize that, but you can't get rid of it. So as it rolls, we know that it will gradually slow down, right? Why does it slow down? It's losing kinetic energy. Where's it going? It's going to heat. So as it rolls, it slows down a little bit. It loses heat. It loses 0.5 joules of heat as it rolls across the table. When it reaches the purple ball, it has 4.5 joules of energy left, kinetic energy. Okay? Then it transfers its kinetic energy to the purple ball. So it does work on the purple ball. So that's negative 4.5 joules for this white ball. It lost 0.5 joules of heat as it rolled, and now its final energy is negative. I'm sorry, the change in energy is negative 5. It's got 0 kinetic energy afterwards. It's just sitting there, it's not moving. So the change in energy from 5 to 0 is negative for that ball because it had energy and it lost it. It lost it in 2 processes, heat and work. Any questions? Which part? It lost heat through 2 processes. I'm sorry, it lost energy through 2 processes, heat and work. So it lost energy by a transfer of thermal energy into the table. That's heat. And then it also lost energy when it collided here. It did work on the purple ball. So it's the sum of those 2 things, heat and work. Let's look at what happens if the table's rough. So here the surface of the table is rough. It's a lot more friction. Starting off with the ball, 5 joules of kinetic energy. As it rolls across this rough table, it's going to slow down faster because it's going to lose more heat. Here it's losing 3 joules of energy to the friction on the table. And if you rub your hands together, they get warm. Why do they get warm? is friction. Friction causes a transfer of energy. It causes heat. So there's friction involved. There's heat being lost by the ball. When it gets over here, it only has 2 joules of energy. So it does work on the ball. It transfers the 2 joules of energy to the purple ball. It lost 3 from heat due to the friction. Its overall change is the same. The change in energy doesn't depend on the path, but the heat and the work do depend. Because here it lost 3 joules to heat, and this purple ball only got 2 joules of work done on it. Any questions?
So the purple ball doesn't have any heat?
Well, we're seeing that all of this kinetic energy was transferred to the ball. Here, so right here it has 2 joules of kinetic energy as it moves. It is also going to lose energy as it rolls. But in the beginning, it just got that work transferred. So it got kinetic energy from the work. Any other questions? So the change in energy for the white ball was the same for both situations, the rough and the smooth table. But Q and W were not the same. They added up to the same thing. So the change in energy as a state function depends only on the velocity of the white ball before and after the collision. In both cases, we started with 5, ended with 0. So Q plus W is the same, even though Q and W are different. They add up to the same thing. Heat is the transfer of thermal energy. This happens when the system and the surroundings have different temperatures. Temperature is a measure of thermal energy within a sample of matter. So heat is a transfer of thermal energy. Temperature is a measure of thermal energy. So heat will flow from matter that has high temperature to matter with low temperature. And that will occur until both objects reach the same temperature. You take a glass of water at room temperature and you put an ice cube in it. There's transfer of thermal energy from the room temperature water to the ice cube. The water gets colder, the ice cube warms up, eventually melts, and the transfer stops when they become the same temperature. You never see them pass each other, right? The water just continues to get colder and the ice cube continues to get warmer. They just always go to the same, okay? That's called thermal equilibrium, when both things are the same temperature, and at that point there's no net transfer of heat. Okay, let's look at an example here. So a cylinder and piston assembly that we are defining as the system is warmed by an external flame. The contents of the cylinder expand, doing work on the surroundings by pushing the piston outward against the external pressure. If the system absorbs 559 joules of heat and does 488 joules of work during the expansion, what is the value of delta E? We are flirting with physics here, is what we're doing. We're learning just enough physics so that we can understand the rest of the chemistry. Well, here's the equation we learned. Delta, wrong end of the pen. Delta E equals what? Q plus W. The change in internal energy is equal to the heat plus the work. And sign matters here. So what's it talking about here? It says the system absorbs 559 joules of heat. So that's Q, right? Q equals 559 joules. Is that positive 559 or negative? Positive, because the system absorbed it. Okay, when my pocket absorbs money, that's positive for me. So this is plus. I'm just going to put a plus there to emphasize that that's positive. And then we've got this other number, 488 joules. it says it does that amount of work. So that's W. Is that positive or negative? That's negative because the system is doing the work. It's not that the work is being done on it. That would be a positive experience. So this is negative. So to find the change in energy, I need to add these two together. So I've got 559 joules plus W is negative, 488 joules. So 559 minus 488, 71 joules. So the system came out ahead there. It overall gained 71 joules of energy. It gained 559 joules of heat and lost 488 joules by doing work. Any questions?